Hello and welcome to Combinational Circuit 7. This one is going to be on adders, subtractors, and multipliers. So to start off, we're going to start with the adder slash subtractor circuit. This circuit, I'll show you right here. So it takes two 4-bit inputs and will either add them together or subtract B from A. So A will be the main one, the primary one, and then B is being subtracted from A. And this circuit can do both. So it'll make the the acceptable range of outputs and inputs is just like the positive and negative numbers that can be associated with, that can be created with 4 bits. So with positive, the greatest number we can create is 7, and with the negative, the greatest number that we can create is -8. So that'll be for inputs and outputs. So like the highest number we could do 5 plus 2, we could do 4 plus 3, but if we try to do 5 plus 3, it's just going to give us -8. Because it can't express positive numbers greater than 7. So we also have this bit extender here. What this is doing is it's saying, so we have this control switch here, and basically this says, okay, do you want to add or do you want to subtract? And this control switch has several different functions. So when we're subtracting, what we're doing is we're adding the negated version of B here. And when we're adding, we're just adding what B actually is to A. And the way this does this is that it says, okay, well, so if we're negating it, we're going to, and it's in 2's complement form. So what that means is that this XOR gate, what we can talk about in a second, this will negate all of B when this is 1, and then we'll add 1 to that. And so that's 2's complement form. That's the definition. And then when we're not, it's saying, okay, well, we'll just leave it normal, and we're not going to add anything. So that's how that works. And this bit extender device is nice because, and we'll have to get into why this XOR gate is acts as a basically 1's complement negator. So basically what it says is that you can envision this B, because it says is actually a 4 binary number, a 4-bit binary number. So it has B3, B2, B1, B0, most significant bit to least significant bit. So again, saying that B3 would be the most significant bit. And it says, okay, well, and then we have this XOR exclusive OR gate. So what it's saying is that when they're different, be true, and when they're the same, be false. And yeah, and then when they're the same, be false. So say that we are going to add here. So we're gonna say it's 0 0 0 0 plus 0 0 0 0, which is gonna give us 0. We can kind of go over how that works. So what this is gonna say is this is gonna be 0, and what this is doing is that it's saying it's creating almost like a control 3, control 2, control 1, control 0. It's just basically saying turn this into a 4-bit binary number, and so it can either be it'll express either 0 0 0 0 or 1 1 1 1. So if it's 1 bit, it'll just make all 4 of the bits what that 1 bit is. So if it's 0, we just have 4 zeros, and so then it'll compare B3 to control 3. And so control 3 is going to be 0, and if B is 0, well, they're the same, so it's going to return 0. Oh, and then it'll be like that for all the rest of them. Say that hypothetically B2 is 1, and this is 0. Well, then it's going to return 1 because these are different. But say this is 1, now it's going to be negated. So say that B3 is 0, and this is 1. Well, they're different, so it'll turn 1, which is the opposite of 0. In this case here. And then say that it's 1, well, this is also 1, so it'll return 0. So in that way, it acts as a negator. It just returns the complement of whatever B is, or what B actually is, depending on what control is. And yeah, the bit extender just makes it so that we can have one switch here versus 4 different switches. So yeah, that's pretty much it. And then we can go on to the multiplier circuit here. This is a bit messier and a bit bigger. So in this one, since we're multiplying, when you multiply two 4-bit binary inputs, you get the result is 8 bits. And so what that means is that we can input 4-bit binary numbers that can go anywhere from 7 to -8. Although here we have it in like hexadecimal, so you can do it in a lot of different ways. But in terms of just like signed binary, it'll be from 7 to -8. And then our output can go from like 255 to -128. We can express much larger numbers with our output than we can with our input, because of just how many bits we have access to. Okay, so here we have our manually wired splitters here. That's how I was able to like shift all of these numbers here. But we could have used a shifter, which is a just like another logic, it's just another circuit structure, another logical operator. And so that would be something that we could replace it with. But in this case, just because it was really easy, we just used splitters to shift everything over by one. Okay, so in this question is, so in Logisim it's like very easy to change the like number of bits that we can use in a device. If we were actually using like a physical circuit, so you know these muxes, we're inputting 4 data bits here. But if we were to do this like in an actual chip where a mux can only take in 1 bit, then it would just be like much bigger and much more complicated. Like I'm sure, let's see, we have another like mux right here. We can kind of use this for an example. So this is like a mux that takes in 4 bits. It'll determine, like it'll pick either D0 or D1, and this is like a 1 input mux. So this is obviously like a lot more complicated than that, even though they're both deciding in between 2 values. And so all it would do is like the physical thing would just be a lot more complicated, and a lot like less organized. So yeah, that's pretty much it. So yeah, I think those are all of the questions. I can sort of like show the utility of this. So we can change this here into signed decimal, just because it's easier for us to read. And we can say, well, what's we gotta use this here. What's 25? Oh, I can't do that because it's 4 bits. So what's 7 times -8? Is that doing that right? It's saying 56. 7 times 7. 49. 7 times -5. Oh. I don't know if that's working incorrectly. Huh. Oh, that's because it's an unsigned multiplier. My bad. Okay, so it's actually fine. This I just can't do like negative numbers, so that's why we're using hexadecimal before. But yeah, it'll be fine. We just have to change this back to hexadecimal, and we are chilling. So we could do, I don't know, say 8 times 6 ends up being 30 in hexadecimal. So yeah, that is all, and thank you very much for watching. Bye bye.